Hi class, this is a lecture on Chapter 16, Digital Radiography from Dr. Stuart Brashon. Okay, so the advantages of digital radiography: more efficient use of time and space and personnel than screen film. Digital radiography eliminates the chemical processing, the inability to enhance an image after it's already been shot, like screen film. Once it's done, it's done. So you're going to reduce your repeat rate. Storage, it eliminates storage of hard copy film, so no big file rooms. And the inability to view images at any time, meaning if they were in the file room, you had to go get them, you had to pull them from archives, things like that. This way, they are on a computer, and computers are easily accessible these days. Okay, now, a slight drawback to digital radiography is it's still fairly new. So the vocabulary worldwide is not standardized or universally accepted. There's different names for the same types of things depending on what country, what manufacturer, things like that. Okay, and there's several different approaches to the three parts of digital radiography that capture an image. The first being capture of the element, second, coupling the element, and third is collecting. Okay, so there's different approaches to each of those steps. Okay, first, capturing element. Okay, the capture element, this captures the X-rays. So in CR, the capture element is your PSP, the photostimulable phosphor. In other DR modes, the capture element could be sodium iodide, cesium iodide, gadolinium oxosulfide, and lastly, amorphous selenium. And I predict there's a lot more out there, but we're only going to really briefly touch on gadolinium oxosulfide, but definitely touch on the other three. Okay, the second step is the coupling element. This is what transfers the X-ray generated signal to the collection element. Okay, in in computed radiography, it was the lens assembly. In other DR modes, the coupling element could be a lens, it could be a fiber optic assembly, it could be a contact layer, or it could be amorphous selenium, okay? And thirdly, the collection element. This collects the energy produced, which is either light photons or electrons, and it collects them and sends them to the computer to be digitized. In CR, it is the photodiode. Okay, in other types of DR, the collection element could be the photodiode again. It could be a charge-coupled device, or it could be a thin film transistor, or TFT. Okay. Briefly, we're going to touch on this terminology called SPR, or scanned projection radiography. And simply what it is it's a CT scout. It was developed by CT vendors. But what's important about this is that it was some of the earlier digital radiographs, okay? The X-ray tube in CT usually spins around in a circle in the gantry, but during an SPR, it was fixed. It's in a fixed position, and the detectors are also fixed, okay? So it's acting like an X-ray tube against a screen film receptor, okay? And this was fascinating to everyone because it's a digital radiograph, and it was obtained with the X-ray beam being collimated into this fan shape and collected on these detectors on the other side, okay, instead of a PSP. So what they tried to do is make a dedicated chest unit in the X-ray department based on this same technology like CT was using, okay? So they tried to develop this device utilizing this technology for a dedicated chest unit. The beam was collimated, okay, through this pre-patient collimator. It was collimated into this fan shape right here, this fan-shaped beam, okay? And then it was hitting after it went through the patient in this linear detector array, okay? Unfortunately, it did not work out so well. There's a lot of blurred images due to the exposure time being too long. However, this technology is coming back since everything is getting faster. and hopefully they can do something with it. Okay, so the first thing we're going to talk about, the first type of electronic device that is being used a lot in digital radiography and very important to digital radiography is charge-coupled device. And this device was developed in the 1970s. It is highly light sensitive. It was developed for the military. It is a silicone-based semiconductor. It is what is used in cameras, in digital cameras, in photography. The CCD has three principal advantages: the sensitivity, the dynamic range, and the size. Okay, the CCD principal advantages, sensitivity being number one, the ability to detect and respond to very low light levels of visible light. Okay. The dynamic range is the ability to respond to a wide range of light intensity from very dim, like it shows here on this graph, very dim optical density, all the way up to very bright optical densities, okay? And then, of course, the size. CCDs are very small, 1 to 2 centimeters, which makes it highly adaptable to digital radiography. Okay, the pixel size is approximately 100 by 100 microns, okay? And please note CCD has higher sensitivity for radiation, so a much wider dynamic range than screen film receptors did. Okay, first type we are going to talk about is cesium iodide paired with the CCD. Cesium iodide, of course, is a phosphor that is used. Sodium iodide is also used, but cesium iodide is what we're going to be talking about. Okay, and this is paired with these CCDs, and what the design that they called it is tiled CCDs. So they tiled this entire surface area with CCDs covered with phosphorus. When the X-rays hit that phosphor and that light is emitted, all of these CCDs can collect all of that light data, okay? So it covers a very large area, so the exposure time ends up being very short, okay? And what I want to note about this illustration here is all these little fiber optic bundles are these cesium iodide phosphor bundles, okay? They're filaments. And they're used to transmit the scintillation light to the CCD array, okay? So it's absorbing light, and it's transmitted to all of these hundreds, if not thousands, of CCDs, okay? Okay, the next type we're going to talk about is cesium iodide with amorphous silicone, okay? The early application of this captured X-ray and transferred to a collection element. Well, the collection element being used here in this example is silicone sandwiched as a TFT, or thin film transmitter, and that's what these little yellow parts here. So the silicone is sandwiched in between these, okay? Now, this semiconductor silicone is usually grown as a crystal. But when they're talking about amorphous silicone, it's a fluid, it's a liquid that can be painted onto surfaces. And that's what this is. So they've painted this on a glass substrate, okay? And so and this is your scintillation phosphor up here. So all of this light that is emitted when the X-rays hit this phosphor here can be absorbed by all of this amorphous silicone here that's been painted on. So that's a huge area that can collect that data so that since it's highly reactive to the light, it'll result in lower patient dose. So more of your X-ray beam is being utilized to make the picture. Okay, this is an up-close picture of that. This is a DR image receptor fabricated into these individual pixels. So this is just blown up one of these pixels right here. So here's one pixel and it's blown up. So this surface right here is supposed to be the amorphous silicone that's been painted on. Okay, this is your thin film transistor. And this is a little capacitor that's going to store all the energy. Okay, so this here is an up-close look at this. So this is one unique pixel right here. And then we have a thin film transistor here. We have a storage capacitor here. We have electronic lines here so that the energy can be conducted here. Okay? So your pixel detector here that can actually utilize the emitted light from the phosphor surface is about 80%. The other 20% is covered up with things that are not light receptive. Okay? Okay, so this is a drawback to DR, if there is any. I mean, this is one. It's a drawback to all of these little CCDs and how they're getting smaller and smaller, okay? So this drawback is the coverage of some of the surface by the electronic components, which are not collecting any emitted light. And the percentage of the pixel face that is sensitive to emitted light is called the fill factor, okay? And you need to know that. So the fill factor is approximately 80% of that surface area. So 20% of the X-ray beam does not contribute to the image. So, and this is one of the dilemmas of DR. So as pixel size is reduced, spatial resolution improves, but at the expense of the patient radiation dose. Because what they want to do is keep the beam intensity consistent. So they have to increase the beam intensity to keep an adequate signal strength. And when you do that, you increase dose. Okay? Now, they've been working on this for a long time to try to fix this. And with nanotechnology up and coming, it looks like they're getting closer. Okay, so this nanotechnology is promising to increase this fill factor space percentage, and which will increase spatial resolution even more, but still have some control over patient dose. So we'll still be able to lower patient dose. So that technology is up and coming. One more thing before we go on. Cesium iodide is also changed out in some manufacturers, and they use gadolinium instead. So the gadolinium can be used same way. It's a phosphor that it will emit light when hit with X-ray. Okay, so I just wanted to let you know they can be swapped out and used the same. Okay, the third type that is used is called amorphous selenium. Okay, but there's no scintillation phosphor used in this one. In this one, both the capture element and the coupling element are the same thing. They're this amorphous selenium. The X-rays interact with the selenium and produce a charged pair. This amorphous selenium, as shown here, is sandwiched in between two electrodes. The top electrode and this what's called pixel electrode. Okay, when the X-rays hit, it makes a charged pair, and this is collected by the storage capacitor and remains there until the TFT reads it. Okay, so that's the third type. Okay, so 4 methods are used to produce a radiograph. Okay, so CR uses photostimulable phosphor to generate a latent image, so it uses PSP. We talked about that in chapter 15. Okay, and then the other 3 methods that we talked about are all used in different types of DR. Okay, cesium iodide coupled with CCDs, cesium iodide and amorphous silicone, and amorphous selenium. Okay, the first 2 methods we talked about in this chapter of DR are indirect processes, simply because the X-rays are converted first to light and then to an electronic signal. The last one we talked about, the amorphous selenium, is a direct process because the X-rays are converted straight to electronic signal. Okay? So this is important. You need to know the difference here. Okay, and to wrap it up, here is just a recapture of digital radiography. So CR is using as its capture element PSPs. The coupling element is the lens fiber optics, and the collection element is the photodetector, the photodiode. Okay? The scanned projection radiography, which we don't really need to talk about anymore, okay, utilized, the capture element was either sodium iodide or cesium iodide. There was no coupling element, and the collection element's a photodetector. Okay? Now, the things we talked about today in this chapter, the indirect types of DR, we're using cesium iodide as the capture element, or gadolinium. Okay? The coupling element was either the fiber optics or a contact layer. Okay, and the collection element was either the CCD or a thin film transmitter. Okay, and this CMOS is just another type of device that collects the energy, and you'll learn more about that when you go more in depth with how a screen is actually made, how a cassette is actually made. So you'll learn more about that. Okay, but for now, all you need to know is about the CCD. Okay, the next type is the direct. Okay, and the direct is using the amorphous selenium as the capture element. Okay, there is no coupling element because remember, in this direct type, the capture element does both things. Okay, the collection element was the thin film transistor. Okay, so you need to know this chart. You need to know the parameters here. You might get a question on which type are indirect, which type is direct, which types use cesium iodide as a capture element, which type element is used in direct, stuff like that, okay? It looks like a good matching question. All right, so several steps are eliminated when we progress from screen film radiography through CR, computed radiography, and then to digital, all digital radiography, okay? So several steps in the patient workflow are eliminated. So we have gotten rid of loading and reloading cassettes. We've gotten rid of processing films in a big film processor with any chemicals. And we've gotten rid of hanging films on light boxes and alternators and things like that. And lastly, we no longer have to file or store all of those films, okay? So more efficient for time, space, and personnel. Okay, and that is the end for Chapter 16 in Bouchon. Okay, and I will see you next week.